Welcome back, Intro to Chem students. So we actually left off talking about what that molecular formula tells us. The next thing that we're going to go through a little more information about covalent bonding and what that is. And then we are going to learn how to draw Lewis structures. That's the next part of this. So, and again, this is in Chapter 8, I believe Section 2 and Section 3 kind of goes through that. So covalent bonding is always that sharing of electrons. We already talked kind of about these characteristics of covalent compounds. They don't form specific crystal structures and all of that. These are just, well, honestly, these are just vocabulary words from the chapter that you'll need to know. Molecule, obviously atoms bonded together, molecular formula, that's what we looked at, this HF, H2O, right? That's the molecular formula. We said it tells us what elements are in there and how many and so on of each type of atom, so that's what a molecular formula is. Diatomic, so dia means two. Diatomic molecules, technically it's any molecule that has two. So, for example, really, this would be a diatomic molecule because it's hydrogen and fluorine. This would be a diatomic molecule. It's fluorine and chlorine. This is not diatomic because it's two hydrogen with an oxygen, so that's not diatomic. But there's some elements that when they don't really like to be alone, let's just say that, and so they don't really want to be by themselves. So when they're bonded together, they're always, when there's, when it's a pure sample of, let's say, hydrogen, I'm trying to think of the best way to word this. If it's a pure sample of hydrogen, it's always two hydrogen atoms bonded together. So pure hydrogen, pure nitrogen, pure oxygen, pure fluorine, chlorine, bromine, and iodine. Whenever we have those substances pure, they are always diatomic. It's always N2, O2, F2, and so on. So when we say diatomic molecules, which elements are always diatomic, we're talking about these that when they're pure and not bonded with another type of element, they are always in that diatomic state. So again, it would be, like when the oxygen that we breathe in the air is this oxygen. It's an oxygen with another oxygen. They just don't ever want to get lonely. It becomes very important from this point on for you to memorize those. There's a couple of cool little ways that I like to remember those. Oh, whoopsie. Sorry, I'm inserting a page so I can show that to you really quickly. There we go. All right, so here's my secret little way to remember those. So we said hydrogen, nitrogen, oxygen, fluorine, chlorine, and bromine. I always remember the rhyme, and I learned this in college, and if you want to make up your own cute little thing, you can. That's whatever helps you. I always remember horses need oats, that's an A, for clear brown, and you're not going to, I realized I forgot one, iodine. And this is weird, for clear brown eyes. Either eyes or eyes, right? Horses need oats for clear brown eyes. That's one way that you can always remember which ones, when they're in their pure state, are diatomic. This becomes really, really important when we are learning to balance chemical equations, which comes later in the year. Like if you don't know when we're predicting products that, oh, oxygen's produced in this reaction, but it has to be O2, you're going to really have a hard time with that. So just from here on forward, please, you're just going to be kind of expected that you know this a little bit. There's one other kind of cool little way to remember. If you look at where these are on the periodic table, let me just erase that really quickly. The other rule is it's 1 to 7 make a 7. So element number 1, actually I can do this on here. Element number 1 is hydrogen. Element number 7 is nitrogen. And then remember we said 1 to 7 and then make a 7. So 1 to element 7 and then make a 7. So over and down make a 7. You will find I did not mention astatine, but a lot of textbooks will not include this one as being diatomic, but other ones will. So it's sort of a whatever. And, you know, I'll never ask you about that one because it sometimes gets included, sometimes does not. So I'm never going to ask you to remember that one. But again, this one you obviously need to be looking at a periodic table, and it's element 1 to 7 and then make a 7. So that's another way that we can kind of remember that. Okay. So as promised, we want to go through Lewis structures today. A Lewis structure is a representation of molecular structure using dots and lines to represent electrons. We remember earlier when we talked about electron dot structures, this is really kind of the next step of using that. So when you guys started your model building kits, that's actually what you were kind of doing. That was an introduction to Lewis structures. So a quick review, because I haven't seen you for a while. How do we know when we do, like, let's say if I wanted to draw the electron dot structure for hydrogen, hydrogen has 1 valence electron, so it has 1 dot. Helium has 2 valence electrons, so it has 2 dots. I like the right-left format. That's not quite, sorry, I'm trying to draw on my screen here. That's not super accurate when it comes to helium, but we're just gonna, whatever, okay? Lithium, so first of all, how do I know how many valence electrons things have? So these electron dots represent the number of valence electrons. And I know we talked about this a little bit. How do we know how many, let me get rid of that, how many valence electrons things have? Well, it's super simple if you look at the periodic table. Everything in group 1 has 1 valence electron. I'm going to write this with my pen. Okay, everything in group 1 has 1. Everything in group 2 has 2 valence electrons. Everything, these transition metals, most of these have 2 most of the time, so we're going to go with the most of the time rule because let's worry about the exceptions later. Everything in, so technically we call this group 1, group 2, group 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This is group 13. Group 13 have 3 valence electrons. Group 14 have 4. 15 have 5. I'm in the way of myself, people. Group 15. Geez, I hope you see a pattern there, right? So yeah, we see 1 valence electron, 2 valence electron. All of these have 2 valence electrons. When we get over into these, this is the P block over here, which it's okay if you don't know that. But group 13 has 3. So these are all like whatever group number they are, minus 10. That's how many valence electrons they have. I know we kind of went over this, but I also know it's been a while. And just remember the format of how we find that out and then how we represent that. So for example, silicon has 4 valence electrons, right? Phosphorus has 5 valence electrons. Carbon has 4 valence electrons, and so on. What that means is, so let's look at carbon really quickly. Remember that it wants to have 8. So if it can pair with things like, it might So hydrogen has one right here. It might share these two. It might bond with another hydrogen here. Whoa! And it could share. Hydrogen has one valence electron, right? It could share with that. And the way we actually would represent these shared valence electrons is as a line. So we really would do boom. This, people, is a Lewis structure. This is exactly our end goal. So one rule that we have, so let's look at this one again, this CH4. So remember that hydrogen has one valence electron, and it will share another electron with something else, so that connects to hydrogen. So the end goal of everything is always to have a stable octet, except if you're hydrogen. Hydrogen really only has room for 2 valence electrons, so it's one of those exceptions to the rule. We have hydrogen is completely satisfied with a stable 2 instead of that stable octet. So it's a little bit different. Here's, I think, the best method for calculating Lewis structures. I want to first calculate how many valence electrons I have total in this molecule. So I need to know I have 4 carbon, 4 hydrogen, not 4 carbon, 4 hydrogen and 1 carbon. All hydrogens have 1 valence electron, so I have 4 times 1 each, which gives me 4, and then carbon has 4 valence electrons. I have a total of 8 valence electrons here. I want to set up a Lewis structure that shows where the electrons are shared and what that molecule looks like. So if I start putting this together, so first of all, carbon has 4 valence electrons, so it has 4 bonding sites, and that's really important. Carbon's going to have to bond with each of these 4 hydrogen atoms in this way. And then I can just connect these shared electrons with a line. Lines represent 2 electrons. Okay, this is a little bit messy. However, so each of these lines represents 2 electrons. The way when we're drawing Lewis structures, I want to calculate this first. So on the worksheet I'm going to give you, I want to see that. And then I want to see how you have bonded these together. When you're done putting these, when you're done building these Lewis structures, I have to make sure I have 8 valence electrons. That carbon is surrounded by 8. The hydrogen can only be surrounded by 1 pair, so 2. Okay, hydrogen needs 2. Since these are shared, I can count this as this is 2 around the hydrogen. This is 2 around this hydrogen, 2, right? We're shared, so we can count it around the hydrogen and around the carbon, 2 around this hydrogen and 2 around this hydrogen. Around the carbon, we need a stable octet. We have that, 2, 4, 6, 8. I've accounted for all 8 of my valence electrons. I am done with this molecule. This is perfect. I know I'm going to run out of time here, so I want to just show really quickly what water would look like. So oxygen had 6 valence electrons. And then this is how, and each hydrogen had one, and this is how it would look as a finished molecule.